Okay, so today we're going to talk about how to master filling in orbital diagrams. In order to understand that, we got to cover a few things in the first place. Now, warm-up question is, in the F block, how many suborbitals are there? What this is asking is how many shapes. And if you know the number of shapes, you also know the number of electrons it'll hold. Okay, there's 7 F suborbitals. Each holds 2 electrons. So they can hold a total of 14 electrons in an F suborbital. Now, we talked about electron configurations in the last class. This is the basics. These are like the first, first 12 elements or something like that. But we're going to go beyond this. But it is important you remember this noble gas shorthand, because we're going to be using this for some of the other examples that you're going to see, the more complicated ones. So here's some of them. So let's take a look at aluminum. Aluminum, if you find it on the periodic table, it should have 13 electrons. It's element number 13. Remember how we do the shorthand. Neon is the noble gas one period above the period aluminum is found in. And then we just go left to right, writing down the s and p orbitals until we get to aluminum. So it's 3s2, 3p1, because we're in the third period, which is the third primary energy level. Now let's look at calcium. So we're going down again. Now we're down to the fourth. So again, take a look. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. That's a lot to write. But if you go up one period, the noble gas at the end of the third period is argon. So we can write the symbol for argon inside brackets, and then we can write 4s2. Because it's only 2 elements into the S block. So that's not too bad. Now we're going into transition metals, and transition metals have a little bit different set of rules. Okay, so for manganese, we've got 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, but do you notice it doesn't say 4d5? It says 3d5. D orbitals always have one less in terms of where their energy level is. They're one less principal energy level than the period they're in. So 3 is proper for the d orbitals in the fourth period. Again, if we're going to write it with the shorthand, it's argon, and then 4s2, 3d5. Don't forget, d's always are one less than the period. And now let's go all the way down to bromine. Bromine, oh boy, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p5. Okay, so we're 4 into the 4p block. Do you notice that 3d10 is less, has a lower number, principal quantum number, well, energy level, than the s and p orbitals that are on either side of it. D orbitals are always one less than the period. So again, we'd have shorthand is argon, 4s2, 3d10, 4p5. So those are more complicated examples, but they're not too bad. Now, exceptions. Just when you think everything kind of is following a like normal pattern and you know what's going on, this is what we would predict for chromium. Chromium is a transition metal, right? So you count it's the fourth element into the D block in the fourth period, but because it's a D, it's one less than the period number. So 3D, fourth element in, 3D4, everything looks great. That's not what it actually is. It turns out that everything fills in order of energy. And it is a lower energy situation for an atom if it can have a half-filled d orbital and a half-filled s orbital. So here you see s is completely filled. D is 4/10 of the way filled. So this is a lower energy situation than that. So it doesn't follow the normal pattern, but it still follows the rules for filling, which you will see in a little bit. So if we were going to abbreviate it, it's argon 4s1 3d5. So not only are half-filled d orbitals special, completely filled d orbitals are special. So if you look at copper, copper is the 9th element in the fourth period transition metals. Again, remember it's fourth period, so the D has one less than 4. This is what we would predict because it's the 9th element. It should be 3d9, right? Well, it also turns out that completely filled d orbitals, stealing one electron from the 4s, has a lower energy. So again, everything fills from lowest energy to highest energy. Now there are other exceptions. These are the only two you need to know. Okay? Argon 4s1 3d10, and for chromium it's argon 4s1 3d5. And you should be able to write the full thing out the long way as well. Okay, on to orbital diagrams. Sometimes they're called electron in a box diagram. So, because you're going to see when I get to showing you what they look like, there's going to be a whole bunch of boxes. And the boxes are going to, each box will represent an orbital or a suborbital, and they'll be stacked in terms of energy from lowest to highest, as you'll see in a minute. And the boxes are filled the same way we write electron configurations. It's just that we have a little bit more detail when we do that. Each box holds 2 electrons because it corresponds to a suborbital or an orbital. And we have 3 rules that help us designate the way to fill boxes. And these are important rules to remember. They're vocabulary. Okay, first one is called the Aufbau principle. The Aufbau principle simply states electrons fill the boxes in order of energy from lowest to highest. Okay, so that's pretty straightforward. I've been mentioning that all along. Hund's rule is every suborbital of a given orbital, so if you've got like a p orbital broken into px, py, and pz, each of the x, y, and z's has to get 1 electron in it before you can add a second one. So you can't put 2 electrons in a px, 1 in a py, and leave pz open. It's energetically unfavorable. Okay? The third thing is the Pauli exclusion principle. Now, what this states is that electrons in the same suborbital, so the same box, must be paired. That is, they must have opposite spin. So I'll show you how we do that in a moment on the next figure. But basically, electrons actually spin and have a magnetic, because they have a charge and they're spinning, they cause a magnetic dipole, like a magnet. And so if you have one spinning one way and the other spinning the other way, they're attracted to each other. But remember, electrons are also negatively charged, so if they get close to each other, they repel. But the magnetic attraction helps offset some of that repulsive force. So they're always going to be paired. Now, here's what an orbital diagram looks like. So we've got increasing energy. Do you notice I've got them stacked? 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, etc. So from lowest to highest energy. All right. The arrows are going to represent electrons. We always add them one at a time until we fill everything in that orbital. And then once the orbital has 1 in every box, we pair them. So this shows, we do them as arrows. An arrow up is always the first one in a box. An arrow down is the second, and we have to pair them. The arrow direction represents the direction of spin. Remember, first arrow always goes up, okay? So if we were to write the electron orbital diagram for nitrogen, let's see, 1s2, 2s2, 2p3, we should have 2 here, and 3 here. This is how we do them. Notice, first one up, second one down. First one up, second one down. Up, up, up. Now, if you add the superscripts, there's 7. 2, 4, 5, 6, 7. That's the right electron configuration. That's the lowest energy ground state configuration, all right, for nitrogen. Now, germanium. Find germanium on the periodic table. All right, you've got a homework sheet. If you flip to the back side of that homework sheet, there is actually, or the second page of it, one of the pages says you can write your own. I think you should try to write germanium in there. And I will pause and wait for you. And then I'll put up what it is and you can correct it. Okay. That's what germanium looks like. All right. It's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p2. And that's the way it would be organized. All right. So hopefully you can do that.